Quantum field theory is a way that scientists use to understand how tiny things in the world around us behave. These tiny things are called particles, and they are so small that you can't see them with your eyes. Instead of thinking of particles as tiny things, QFT thinks of them as tiny ripples and fields that fill up all the space around us. You can think of these fields like the ocean, and the particles as tiny waves in the ocean. Scientists use QFT to understand how these particles move and interact with each other. They also use QFT to study how different types of particles can come together to make bigger things, like atoms, molecules, and even planets. QFT is really important because it helps us understand how the world around us works at a very small scale, and it also helps us make new discoveries about the universe. Imagine you're playing with a ball in a swimming pool. When you throw the ball, it creates ripples in the water. These ripples are like the waves in the quantum fields that QFT describes. The ball is like a particle, and the ripples it creates are like the waves that surround it. Another example is light. When you turn on a flashlight, it creates a beam of light that you can see. But what you can't see are the electromagnetic waves that make up the light. These waves are like the quantum fields that QFT describes, and the light particles are like the ripples in those fields. Finally, think about the air around you. It seems empty, but it's actually full of molecules that are bouncing around and colliding with each other. These molecules are like particles in the quantum fields, and the collisions they have are like the interactions between particles that QFT describes. In quantum field theory, particles are not just tiny balls, but they are actually waves in the fields that fill up all of space. There are many different types of particles that can exist, and scientists give them names based on their properties. For example, there are particles called electrons, which are negatively charged, and particles called protons, which are positively charged. These are the particles that make up atoms, which are the building blocks of everything around us. There are also particles called photons, which are particles of light. These particles don't have any charge, but they can carry energy and move at the speed of light. In addition to these particles, there are many other types of particles that scientists have discovered or predicted, such as neutrinos, quarks, and W and Z bosons. Each type of particle behaves differently, and scientists study these particles to learn more about how the world around us works. For example, studying electrons can help us understand how electricity and magnetism work, while studying photons can help us understand how light behaves. So in short, QFT describes many different types of particles that make up everything around us, and scientists study these particles to learn more about how the world works. In quantum field theory, particles are described as excitations of underlying quantum fields that permeate all of space and time. These particles are grouped into two main categories, fermions and bosons. Fermions are tiny particles that make up the world around us. They are one of the two main types of particles in quantum field theory, which is a way that scientists study the tiniest things in the universe. Fermions are special because they have a property called spin that makes them act differently than other particles. You can think of spin as a top spinning around. Because of this spin, fermions are very picky about where they can be in space. For example, if two fermions try to be in the same place at the same time, they push each other away. This is called the Pauli exclusion principle, and it's what gives atoms and molecules their structure and stability. Fermions are particles that have half-integer spin, which means they obey the Pauli exclusion principle, and therefore cannot occupy the same quantum state simultaneously. This leads to the phenomenon of electron shells and is responsible for the stability of matter. Examples of fermions include electrons, quarks, neutrinos, and protons. Fermions include particles like electrons, which are responsible for electricity, and quarks, which are some of the building blocks of protons and neutrons. Without fermions, the world around us would look very different. Bosons are tiny particles that are different from fermions, which are another type of particle in the universe. Bosons are important because they carry the forces that hold everything together. You can think of bosons as messengers that carry information from one particle to another. For example, photons are bosons that carry the electromagnetic force, which is what makes magnets stick to the fridge and powers all of our electronic devices. Unlike fermions, which are very picky about where they can be in space, bosons are happy to hang out together in the same place. In fact, they like being together so much that they can all be in the same quantum state at once, which is called Bose-Einstein condensation. Bosons are particles that have integer spin, which means they do not obey the Pauli exclusion principle and can occupy the same quantum state simultaneously. This leads to phenomena like superconductivity and superfluidity. Bosons include particles like photons, W and Z bosons, and gluons. Without bosons, the world around us would be a much less cohesive place. There are also particles that have been predicted by theory but have not yet been observed experimentally, such as the Higgs boson, which is responsible for giving mass to other particles. Quantum field theory is a theoretical framework that combines the principles of quantum mechanics and special relativity to describe the behavior of particles and fields at a microscopic level. In QFT, particles are not treated as isolated objects but rather as excitations or vibrations of underlying quantum fields that permeate space and time. The basic idea behind QFT is that particles are created and destroyed through interactions with these fields, which are characterized by their energy, momentum, and other quantum properties. These fields are described by mathematical functions, known as wave functions or field operators, that evolve over time according to the laws of quantum mechanics. In QFT, the fundamental particles and forces of nature are described in terms of a set of interacting quantum fields. The most familiar of these fields are the electromagnetic field, which describes the behavior of light and other electromagnetic waves, and the Higgs field, which gives mass to particles like the W and Z bosons. One of the key predictions of QFT is the existence of virtual particles, which are particles that can spontaneously appear and disappear within the constraints of the uncertainty principle. These particles can have measurable effects, such as the Casimir effect, which arises from the fluctuations of virtual particles in the vacuum. QFT has been successful in describing a wide range of physical phenomena, including the behavior of elementary particles, the structure of atoms and molecules, and the properties of materials. It is also an essential tool for understanding the behavior of high-energy particles in particle accelerators and in cosmology, where it is used to model the early universe and the behavior of black holes.